Hi guys, this is Mrs. Rooker. For those of you who don't have me as a teacher, I am in room N2. You're welcome to come by and get help at any time if you want to, or just say hi, whatever. So we're going to get started on today's video. This is actually not a notes video today. You don't have notes associated with this section. It's just homework. So what I'm going to do is just go through a couple of the homework problems with you. So you should be kind of working on these with me as we go along, and then you'll be responsible for finishing the homework on your own or in class. All right, so let's get started. In exercises 33 through 38, use the intermediate value theorem to show that each polynomial has a real zero between the given integers. And then you were supposed to do numbers 35, 37, and 39 in this little section. So I'm going to go back to the notes from the last video, where it talked about the intermediate value theorem, and that is let f be a polynomial function. If f of a and f of b have opposite signs, then there is at least one value c between a and b that is a zero. So what that means is, we do this problem. If we plug in -1 and get an answer, and we plug in 0 and get a separate answer, if one of those is positive and the other is negative, then that means there must be a solution or a zero between 0 and 1. It must cross the x-axis somewhere between those two. So if we have, So we'll just go ahead and do this problem. So we're going to plug in -1, we're going to plug in 0. You can do this two different ways. You could do direct substitution, which is the way I expect most of you to do. That just means you take this number and you replace x with that. It's kind of the old school method that we usually work with. Or you could use synthetic substitution. I'm actually going to do that on for the -1, just because we're going to be doing synthetic division in the next video, so I want to get you kind of exposed to that a little bit. So this is something you learned in Algebra 2, but we're just going to review it. Synthetic substitution means you're going to write out the coefficients of the polynomial, but you can't skip any degrees. So you can see here that this is 4th degree and this is 2nd degree. We skipped 3rd degree there. So what you're going to do is you're going to put in a little plus 0x to the 3rd so that we're not skipping the 0 degree. And then it goes from 2nd degree all the way down to a constant, which is technically 0 degree. So I'm also going to add in a plus 0x in there. Okay. So then I write this all the coefficients out. So it's going to be 2, then 0, then -4, then 0, then the last one is 1. So write out the coefficients, and then the thing that I'm substituting in will go on the outside. So the -1 will go on the outside. All right, the first step in synthetic substitution is just to bring the first number down. And then it's always the same pattern. We multiply and then add straight down, multiply, then add straight down. So we'll multiply -1 times 2. -1 times 2 is -2. And then we add straight down. 0 plus -2 is -2. Then we multiply again. -1 times -2 is +2. Then add straight down. -4 plus 2 is -2. Then multiply again. -1 times -2 is +2. Add straight down, we get 2. -1 times 2 is -2. Add straight down, I get -1. Now this is the only number that I care about when we're just doing substitution. So really, this is all I care about. That's my answer when I sub in -1. All right, you could also do 0 the same way. You could set it up like this, 2, 0, -4, 0, 1, and then do 0 here. Or you can do direct substitution, which I think would be a lot quicker since you're working with 0. 0 times anything is 0, minus 0, plus 1 would just give us 1. But I'll do it synthetic division, the synthetic division way as well. 2 times 0 is 0. Add straight down, we get 0. 0 times 0 is 0. Add straight down, I get -4. 0 times -4 is 0. Add straight down, I get 0. 0 times 0 is 0. Add straight down, I get 1. And again, that's the only number that I care about. All right, so back to the intermediate value theorem. Since one of these values was negative and the other one was positive, it must cross the x-axis somewhere between those two numbers, which means there is a 0 or a solution between -1 and 0. All right, so you're going to do that same thing on 37 and 38. Basically, just sub in, and one of them better be negative and one of them better be positive to show that there is a 0 between the two of them. All right, so we're going to move on to the next few problems, which have a lot of directions. So we're just going to go through, we're going to do 41 together. Let's see. Use the leading coefficient test to determine the graph's end behavior. So this is the first term. This is all we need to look at to determine the end behavior. Since it's an odd degree, we know the ends are pointing different directions. I know that a cubic function looks something like either this or this. And then the leading coefficient is what tells me if it's going to be starting down and going up or starting up and going down. Since this leading coefficient is a +1, that means it's going to start downward and then finish upward. It's kind of like a positive slope. Think about a line with a line with a positive slope. Starts down and goes up. Same kind of idea with this. It's starting down and going upward. All right, so it is not this one, it's that one. So that's our answer for A. And then B, find the x-intercept, state whether the graph crosses the x-axis or touches the x-axis and turns around at each x-intercept. So multiple ways we can find the x-intercepts. You could use a graphing calculator to do a lot of this, but be careful because you might not see some x-intercepts that are actually there if you just use your graphing calculator, especially if they're decimals or obviously imaginary zeros you're not going to see on the graphing calculator. So I'm going to do all of this by hand right now. So for B, to find the x-intercepts, I'm going to factor. So I'll do that here. So we have x cubed plus 2x squared minus x minus 2. So since this has 4 terms, I am going to use factor by grouping to factor this. There's no GCF I can take out first, so I'm just going to jump straight into factor by grouping. When I factor by grouping, I put a line down the middle. Some people use parentheses to kind of group them ahead of time. All right, and then I look just at the first 2 factors, or the first 2 terms, sorry, and find the GCF between those 2. The GCF is going to be x squared. When I factor out a GCF, I'm left with x plus 2. Now I know when I'm doing factor by grouping that I want to end up with the same thing on both sides, so I'm just going to kind of work ahead and copy that over here. I know I want x plus 2 in parentheses twice. And then I look at this side and I determine what has to be factored out of negative x minus 2 to give us x plus 2. And the answer is a -1. And then the thing that I have 2 of, sorry, my pen stopped working. Oops, there we go. All right, the thing that I have 2 of, this x plus 2 becomes one of my factors. And then my other factor is the things left over, the x squared minus 1. All right, and then I can set each factor equal to 0 to solve, or I could factor this one further. This is a difference of squares, so it'll be x plus 2, not 2, sorry, x plus 1, x minus 1. And then this will stay just x plus 2. Set each factor equal to 0. This will give us -2, -1, and +1. So if you're going to write these as x-intercepts, you might want to write them as, sorry, the pen is not working very well, as -2, 0, -1, 0, and 1, 0. So write them as coordinate points. All right. Oh, and then we are also supposed to state whether it crosses or touches and turns around. Since we don't have any multiplicity, meaning we don't have any repeating zeros, they're all different numbers, they all must cross at that point, like this, like that, instead of just touching and turning around. So they're going to cross, not touch and turn around for each of those. So cross. So they're going to cross the x-axis at all of them. All right, find the y-intercept. So this one's pretty straightforward since it's in standard form. The y-intercept is just going to be the constant on the end. So C, the constant is 0, -2. You could also, if you didn't remember how to do that, you can just plug 0 in for all the x values, and that'll give you your y-intercept. All right. Determine whether the graph has y-axis symmetry, origin symmetry, or neither. So on this one, I'm actually going to kind of start graphing it a little bit since I have some information, and that'll help us to determine the answer to D. So I'm going to zoom out a little bit. So to graph this, I've got zeros at -2, -1, and +1. And I know it's going to start downward and go upward, and then I know that the y-intercept should be at -2. So it's going to look something like this. All right, so determine whether the graph has y-axis symmetry. So y-axis symmetry means, this is the y-axis, that it would, if I folded it over the y-axis, it'd be the same on both sides. Hopefully you can see it's not symmetrical to the y-axis. Origin symmetry means if you were to rotate it 180 degrees around the origin, you would end up with the same image. So a little bit hard to do, but if I were to rotate this around the origin, this part would now be this would be facing up. This part over here would now be facing upward, and it would look something like this, which isn't the same as what I have. So it's not symmetric about the origin either. So this is going to be, the answer to D is going to be neither. Which means this is not an odd function or an even function, it's neither. Because if it's symmetric about the y-axis, then it's even. If it's symmetric about the origin, then it's odd. This is neither even nor odd. And I know that actually just by looking at the function itself, because if you look at all the degrees of the function, you've got even and odd degrees. 3's odd, 2's even, and so on. So it can't be even or odd, it's going to be neither. All right, and then if necessary, find a few additional points and then graph the function. We're not too worried about finding a bunch of additional points. You can find some more, but I'm happy with just this as your answer for E. Sorry, come on, pen. It's the answer for E. And then it says use the maximum number of turning points to check whether it is drawn correctly. So to find the maximum number of turning points, you look at the highest degree, which is 3, and then you subtract 1 from that. So that means it can have 2 potential turning points. And turning points are just like they sound. This is a turning point, and this is a turning point. So as long as we don't have more than 2 turns in there, then we're good to go. And then, yeah, you can always check this by graphing it in your graphing calculator, and hopefully it looks pretty much the same. All right. I think we can do, let's do number 43 together next, and then I'll have you do the rest on your own. So, same idea, we're going to determine the end behavior first. My pen would work. Sorry, it's running out of batteries. I need a new battery. 43A. Determine the end behavior. So it's an even degree, which means the ends are both pointing the same direction, and it's positive in front, so they must both be pointing up. So it's going to look something like maybe that, or it doesn't necessarily need to have all 3 turns. It might look something like that. But the ends will both be pointing up. So the end behavior is going to be as x approaches negative infinity, the function is going to be approaching positive infinity, because as x approaches negative infinity means as we go to the left, the function's pointing up. And then x approaches positive infinity means as we're going to the right, the function is again going upward. That's something I forgot to do on A. I drew the graph, but I didn't write the end behavior. This one, as the function approaches the left side, so, as x approaches the left side, so negative infinity, the function approaches downward, so also negative infinity. And then the left side, the right side, as x approaches positive infinity, the function's also going up. So the function approaches positive infinity as well. All right, so that's our end behavior. B says find the x-intercept, state whether the graph crosses the x-axis or touches the x-axis and turns around. So again, I'm going to factor this. So I have x to the 4th. I believe that says minus, minus 9x squared. So the first thing I'm going to do is factor out a GCF. The GCF is going to be x squared. I'm left with x squared minus 9. And then x squared, this is a difference of perfect squares, so x plus 3 times x minus 3. And then set each factor equal to 0. So I end up getting x equals 0. And I get that twice because this is x squared, so that's the same as x times x. So I get 0 twice. You could write that as a repeated root, or you could actually write it out twice if you want. And then here I get negative 3 and positive 3. And it was a 4th degree, so I should get 4 zeros. So it makes sense, hopefully, that I have a repeated root here. All right, if I have a repeated root, that means that it touches and turns around at 0. But then it actually crosses the x-axis at the other 2. All right, and then once I find the y-intercept, then I'll do a rough sketch of this graph. So C asks for the y-intercept. So if you look at this, there is no constant on the end, and this is in standard form, so the constant must be 0. So the y-intercept is at the point 0, 0. You could get that by just plugging in 0 for x also. All right, so let's sketch this. That'll be our answer for E, is the sketch. So let's do that. All right, so we have a 0 at 0, also at -3 and +3. Okay, and we know our end behavior is that both ends are pointing upward, so it's going to look something like this. Because at 0 we had a repeated root, so it's just going to touch and come back downward. All right, and then D, so I'm going to go back to question D. It said to determine whether the graph is symmetric to the y-axis, origin, or neither. So this appears like it is symmetric to the y-axis. This is your y-axis. If I were to fold it over the y-axis, I would get the same graph on both sides. My picture isn't very pretty, but it should be symmetric to the y-axis, which means it should be an, let me write this, y-axis symmetry, which means it should be an even function. I know it doesn't actually ask for that here, but it should be an even function. And if you look at this, the original function, both degrees were even, which is kind of a way of knowing that it's an even function. You can't always rely on the degrees if you're working with functions that aren't just regular old polynomials, then it's much more complicated. But yeah. All right, so I think that's all I'm going to do today. You guys should finish the rest of the homework on your own or in class. All right, thank you guys.